Good evening, ladies and gentlemen, and welcome to the first lecture of the 2021-2022 lecture season for the RENA and IMRS Southern Joint Branch, which will be on brittle fracture in steel ships. Before we move on to the lecture part of the evening, just do a couple of bits of housekeeping. First of all, for those of you who haven't attended one of our Zoom lectures before, we do a Q&A session at the end. And if you want to ask a question, you can do this in two ways. You can either post a question in the Q&A chat box and it'll be get read out and then responded to, or you can raise your hand, at which point you will be promoted to the level of panelist and allowed to talk. But advance warning, this lecture is being recorded. It will be put on YouTube. So if you don't want to appear on YouTube, it might be best to just type your question into the chat. So as I said, tonight's lecture is on brittle fracture in steel ships, and the speaker is actually me. So I will tell you a little bit about myself first. So my name's Lizzie. I graduated in 2007 from Newcastle University with a degree in naval architecture. I then went to work for Lloyd's Register, where I've had a variety of roles from field surveying to plan appraisal. And then I moved into structures rule development, which is where I now work. And I've done a variety, worked on a variety of various projects over the years, but I suppose most relevantly to tonight's lecture is a recently completed project looking at trying to minimize the risk of brittle fractures in container ships. And that's kind of where my interest in this topic came from. So I'm just going to share my screen. So bear with me for just a second. Let's bring that up. Okay, I really hope you can all see this. I don't have a co-host tonight to tell me if you can. So the purpose of tonight's lecture is to provide more of a sort of a general interest overview of the subject, rather than sort of in-depth fracture mechanic type equation slides, which I don't think any of us really want to see on a lovely evening like tonight. So, I'll talk about what brittle fracture is, and also what causes it, and I'll illustrate what causes it through the use of various historical examples. I'll then look at how the industry has addressed this issue through like the use of different steel grades, and then more specifically then start looking at brittle fracture in container ships, and then the kind of the two main approaches now towards addressing brittle fracture. And then finally I'll talk about some outstanding issues, I think matters that still need to be considered. So what is brittle fracture? So quite simply, brittle fracture is the sudden, very rapid cracking of a material under stress, where you see very little plastic deformation. So you can see I've got a ductile example where the material kind of, a bit like chewing gum, you pull it and it stretches and then eventually fails. With brittle fracture, it just snaps. So a bit more like a hard caramel type thing. The cracks themselves, they're usually initiated a stress concentration, such as a pre-existing material defect, or a defect which might develop in service, such as from fatigue. And then the cracks will continue to grow, and they'll increase in magnitude once they're initiated, running perpendicular to the applied stress. Now, in ductile failure, the material starts to deform plastically once yield is reached, and will continue to deform until you hit the UTS. But in fatigue failure, there's just no ductile behavior before failure. The fracture is very clean and very sharp, and you don't have much warning that it's going to happen. So factors leading to brittle fracture, they can include things like having high yield strength steels, and I'll talk more about that a bit later. Low temperatures, which can cause a ductile to brittle transition. You could have, you're overloading it, so high loading rates, high stresses. If you've got stress raisers that result from flaws or cracks, and then also the material itself could have low fracture toughness, or even the grain, the crystal grains of the structure itself, if they're quite coarse,
that can also increase the possibility of brittle fracture occurring, and I'll talk a bit more about that one later as well. And as I said before, brittle fracture failure is instantaneous, and it can have some catastrophic consequences. So, historical cases. I think we've all heard of the Liberty ships. They are one of the most famous examples of brittle fracture. These ships, they were thrown together in World War II over in America, in a great hurry. They are also some of the first ships to be welded, which becomes quite important later. So these ships, some of the early ones, they developed cracks in the decks and the hulls. 3 of them catastrophically split in 2, where the crack basically went all the way around the girth of the ship. And so this is the Schenectady, and she broke in 2 whilst moored alongside for outfitting. So that was quite an extreme example, and you can just see it's snapped into. So they needed to try and figure out what happened. So the Ministry of War Transport, which was kind of the department at the time in Britain that was in charge of ships, they did some testing on an actual ship, and it was a woman called Constance Tipper at Cambridge University, and she was kind of running this whole thing. And things that they found was that because the ships were sailing in the North Atlantic in winter, they were being exposed to temperatures that could fall below the critical point where the steel changed from being ductile to becoming brittle. So that allowed cracks to start easily. Because they were using welded construction, that allowed the cracks to propagate from plate to plate, whereas in a riveted plate, you get to the edge of the plate and there's nowhere for the crack to go. They get arrested when they hit that edge of the plate. And they also, because of the quite poor design of the hatch corners, they had square hatch corners, and they also had weld seams located close to the hatch corners. And that also meant that you had stress concentrations at that hatch corner that then went into the weld, and then that kind of went all the way down the weld, and then you all the way around the ship. Then combine that with the fact that because it was a war, the ships were often overloaded, and then again they were sailing in winter, so they were subjected to storms. So all these things combined together didn't make for very good design against brittle fracture. Some of the things they did to address this was they changed the hatch design and they reinforced the ships, which did reduce the number of fractures observed. So moving on, this ship is the MV Kurdistan, and she was built by Swan Hunters in 1973. She was built to an ice class. At this time, it was called Ice Class 1, which is not what I think was the highest level ice class at the time by that class society. And she was longitudinally framed, but the sides were transversely framed, and had 6 cargo tanks and was built almost entirely of grade A steel. So she was probably sailing in sort of Canadian waters. So she left Nova Scotia going to Quebec. So she was sailing in the Great Lakes, and she was carrying heated cargo for the first time. So for the ship, the weather conditions were quite poor. The ship was rolling quite heavily, and she was traveling through ice, and which may have caused some damage. As she cleared the ice field, the crew heard a bit of a thud, a bit of a shock, and oil started to leak from a vertical crack in the sides of the number 3 wing tanks. And these cracks came up to about 3.6 meters below the main deck level. So they're quite big cracks. The crew took remedial actions, and the ship continued on. They did things like they transferred oil from number 3 wing tanks, number 4 tanks, but then they felt a second shudder, and they halted that oil transfer. And the weather conditions had improved by this point, but by 9:30 the ship had broken in 2. And basically between the first fracture and the ship breaking in 2, it was about 8 hours. So it was quite quick. So the Transport Canada, they investigated this, and they found that it was due to a brittle fracture. There was a defective butt weld in the port bilge keel. The bulb plate was misaligned, the crack arrest hole was missing, and thermal stress calculations sort of indicated that there was a tensile stress in the shell and the bilge keel resulting from
the carriage of the warm cargo in a cold sea. So you sort of had this thermal stress issue. That combined with impact stresses on the impact loads on the bow meant that you had an overload of the bilge keel and it fractured. So this is like the combination of poor weld metal toughness and high stresses in the presence of a defect. And actually, when they didn't quite establish the sequence of the failure, but they did identify that it was due to this low temperature, high temperature transition, and the weld defects. So the next one, this is also quite a famous one. This is MV Lake Carling. She was a handy-sized bulk carrier built in 1992. Again, this is in North America. She's crossing the Gulf of St. Lawrence. So she was also ice class, strength for heavy cargoes. She had grade A side shell, but the shear strake and strength deck were grade E. And all the steel grades did comply with the class rules at the time. So from that perspective, you know, she complied with the rules. There was a minor crack in the hull and it turned into a 6-meter hull fracture. So the crack initiated at the base of the web frame at frame 91. On the port side, they did find similar cracks at other locations. And the calculations carried out showed that the original crack was as short as 10 centimeters. And so the question was why did it then lead to this massive 6-meter long hull fracture that they had to arrest using drilling a hole through it? So they'd looked at it. The vessel's properly loaded. The seas were calm. Yeah, temperature only -6 degrees. It wasn't that cold. But when they looked at the material itself, they found that the fracture toughness and the grain size of the steel were below kind of, there wasn't an official industry standard at the time, but they were below kind of the average values that you would see for grade A steel at that time. And this is a quote from the accident report. It said, the steel performed below expectations and did not provide a reasonable damage tolerance in all its operational conditions. So this is a case of where the material itself was just poor quality, and that led to the brittle fracture. So the next case, this is a bulk carrier built in 1972. The hull was grade A, the deck and shear strake grade D. She was strengthened with heavy cargoes. She was going through severe weather conditions and broke in two. This is a lovely picture extracted from the accident investigation report, where you can see definitely broken into. So what happened here was that the deck, they found that the deck transverse at frame 78 inside the number 5 port upper wing ballast tank had been damaged. The face flap boundary stiffening was detached, extensively buckled. They found the deck longitudinals completely detached from the underside of the main deck plating. And crucially, the fractures at the end of these longitudinals showed no plastic deformation and were at 90 degrees to the normal deck plating surface. So I think you can just about kind of see, you know, you can definitely see the buckling. You can just about see that the brittle fracture, but there's more pictures to come. A close-up examination showed that there were several small clam-shaped fissures, which is a typical characteristic of fatigue fissure damage. And they were also corroded, which indicated that these had been there for quite some time before the accident happened. And the initiation and rapid propagation of the brittle fracture across the main deck at this location is consistent with previous experience of such discontinuities. So then you can see here that you've got more of these clamshell shaped markings in this bit here, and Transport Canada found that this was their location in the principal line of structural failure indicated that they'd contributed to the concentration of localized stress levels in excess of those which the bottom shell plating could physically withstand. That said, she'd been sailing around for quite some time with these fissures, so why did she fail? Why did the ship break into it in this particular day? So the vessel routinely sailed with a light draft forward. The minimum draft forward for the vessel was supposed to be 4.6 meters. The actual draft forward was 3.7 0.07 meters when the ship left Rotterdam. She was crossing the North Atlantic in winter, but the number 4 hold ballast hold wasn't filled with ballast as it should have been. So this would have left the vessel vulnerable to pounding and slamming. One of the typical solutions for if a vessel is slamming is to increase the draft forward through the use of ballast. In addition to that, the ballast tanks themselves had been damaged previously. There had been quite a lot of structural repairs that were required to the ship that weren't carried out before the ship left Rotterdam. Basically, fractures in the boundaries of the open wing ballast tanks have been discovered, and they were being repaired during the voyage, but the repairs themselves hadn't been completed by the time of the accident. You then combine that with the fact that the weather conditions were quite rough. So you can see here they had sort of very high waves, and they had a violent storm, exceptionally high waves, and another day, January 4th, 2007, another violent storm, more high waves. This day's okay, moderate waves, but you can see that the weather conditions were pretty rough. And so sort of at midnight on the 16th of January, the ship encountered large and steep irregular waves, and these reportedly caused slamming the forward end, and there was a loud bang and severe hull whipping and vibration. And then at 4:30, so there was loss of longitudinal structural integrity initiated by the rapid brittle fractures that had appeared in way of the existing damage near midships. There was then bottom structural failure, which resulted from suddenly imposed compressive loading and localized stress concentrations, which then caused the hull to break in two. So this was a case of the ship wasn't being properly operated in the first place, and they were playing a bit fast and loose with their repairs as well. And then that led to a case of overload essentially on the ship, combined with some structural damage that already existed. So you can see from all those various different historical cases the different means by which you could end up with a brittle fracture in the ship, be it from stress raises, from defects, from overload, from low air temperatures, poor quality of material. All of these different aspects need to be thought about in order to reduce the risk of brittle fracture. So if we move on to fracture toughness requirements, so this is about the material itself. So we'll talk about improving the quality of the material first. So obviously we're talking here about the Sharpie V-notch impact test. This was established in the 1950s, and in 1954 DNV were the first class society to introduce the Sharpie test. By 1959 IACS, so covering all the different classes, all the main class societies, introduced the Sharpie test requirements, but this was only for grades D and E. And by 1970s the standards had risen, but we're still getting brittle fractures, as evidenced by MV Lake Carling. And by the 2000s, there was a minimum standard for grade B, but there still wasn't one for grade A. And actually LR had a standard for grade A, but the standard wouldn't have been sufficient to prevent MV Lake Carling. That's quite important to note. So the main problem though is that it's quite difficult to get accurate and reliable correlations between Sharpie energy and fracture toughness. So that's something else to bear in mind there. But we can look here. So in 1979, as you can see, we've got some requirements for these grades, but we don't have anything for A and B. And this is just kind of looking at IXUR W11, which is provides the standard for hull structural steels. By 1986, we've got a few more. We've got an average energy requirement here. We've got a test temperature requirement. Still nothing for grade A. Move on to 1995. We've now got a range of thicknesses. So we're starting to look at the thickness of the steel as being quite important, as well as the average energy in the test and the test temperature. But again, still nothing for grade A. And then 2004 is when we see, this is pretty much basically what we've got now for these standard grades. So we've got sort of grade A is now covered, but it's important to note that now we're relating the thickness to the average energy for the test and looking at both longitudinal and transverse directions. And we also have even lower temperature requirements as you go up from grade A to grade E. But it's not enough to just specify what the material properties should be. We also have to look at how the steel grades are intended to be used. So IACS has another unified requirement, which is URS 6, which was introduced in 1979. And what they do is they divide different structures up into stress classes of 1, 2, and 3, and that's based on the criticality of the structure. So, so for example, here you have a build strake in the ships for ships with a double bottom, overfull breadth and length less than 150 meters. You can see here that class 2 is within the 0.6 L midships and class 1 is outside. So class 2 is a more onerous requirement than class 1. And then for larger ships and for single bottom ships, we've now got class 3 within the midship region, and then class 2 kind of then tapering to class 1. And this material grade that you use in a particular location is dependent on the stress class and the material thickness. So you end up with this where you've got, so looking here, for example, if you've just got sort of non-critical structure that's less than 15 mil thick, then using grade A is perfectly acceptable. However, if you've got really critical structure and it's 50 mil thick, we're moving to grade E and grade EH. So these materials are getting tougher as we are sort of, the more critical they are and the thicker they are. We also have in URS 6 requirements for low air temperatures. If you remember that I said that one of the problems, one of the leading causes of brittle fracture is if the steel's exposed to very low air temperature. IACS introduced this basic table after MV Lake Carling. It was imposed on them by Transport Canada that they had to sort this out. And so here you can see that we have sort of the lower the air temperature gets and the thicker the steel gets, the tougher the material gets, the higher the grade. Basically, you go from grade E here and you go to grade E, and actually you can't even have minus 55 degrees C and 35 mil thick plate. You're just not allowed to do it. You have to go to grade FH here. You can't even have just standard steels. So that's basically how all the IACS class members are controlling the use of steel grades. However, this doesn't cover all eventualities. We then have to look at kind of more non-standard uses. So that leads us on to brittle fracture in container ships. So as you can see from this, this shows the increase in size of container ships over the years. So you can see this, I think I created this in 2018, which is why it only goes up to 2018, but you can see there's been a rapid increase in the size of container ships. And what this has meant is that the required plate thickness for the upper hull girder has increased dramatically because the stresses have increased a lot. And in order to reduce that plate thickness, high tensile steels have, the use of that's increased. And you can see here that this plot showing hatch coaming side plate thickness, and these are the different steels. And as we get bigger and bigger ships, we're starting to see, so down here we've just got YP32, so you know that's is high tensile steel, but it's not that high tensile. We move on to YP36, but then by the time we get up to 20,000 TU, they're using YP47. So that's got a yield stress of 460 newtons per meter squared. So the trend has been, as the ships got bigger, to use higher and higher tensile steels. And the problem, though, is that these container ships also have very high tensile loads in the upper deck region. And so you're combining very, very high loads with very high strength steels. And as a result, this can lead to brittle fracture. So we have here, just like this is just showing you're because the container ships are normally hogging. That means that the weld seams of the upper hull girder are normally being pulled apart rather than being compressed. For those of you who are familiar with fracture mechanics, when you compress a crack, you do slow the rate of growth, whereas if you start pulling it apart, then you increase the rate of growth. So this is another reason why this is a particular problem for container ships. And so the other problem is that as a material gets thicker, it is more likely to experience brittle fracture than ductile fracture. And also, as the strength of the steel gets increases, you're more likely to see brittle fracture versus ductile fracture. So if you have both an increase in high strength, in the yield strength of the steel, and you also have an increase in the thickness of the steel, then you're increasing even more the possibility that you could experience brittle fracture. And so that then combined with the presence of welding imperfections, which could lead to fatigue damage because you've also got high cyclic loads, does mean this is a particular issue for container ships. So when we think about container ships, IACS have introduced a unified requirement, which is UR S33, that does look at this problem. And in that UR, we consider two cases. So we consider the case where you might have a brittle crack running along the butt joint of the block, or even the subblocks. And then also you could have a brittle crack initiating in that joint, but it would deviate away from the weld and into the plate, or where if you've got other weld attachments like the longitudinal stiffeners, you could have a brittle crack initiate from one of those welds, and that could also propagate into the plate. So IACS basically suggests kind of measures that you can use to try and reduce the risk of the brittle fracture. So the first kind of approach you can really take is you can design for crack arrest. So you assume that a crack will initiate and it will propagate, but something about the design of your ship is going to prevent that crack from leading to the loss of the ship. Its propagation, its growth will be halted by something. And that something could be, you could use various different mechanical measures. So you can do something called block shift, where you, instead of having sort of the weld for your hatch combing in line with the weld of your upper deck, which is then in line with your side shell, you can offset these. So if you have a weld that's initiated in your hatch combing butt weld, it will then get halted by the plate instead of going into the weld seam of the upper deck. You can also drill crack arrest holes, and again, these will halt a crack in the weld. And you could also use crack arrest insert plates, which will also do the same thing. And then to kind of where you've got the crack going into the parent material itself, that's where you then use crack arrest steel. So you don't really want your crack initiating in your weld and then deviating into the plate and then going all the way through the plate and causing lots of brittle fracture. So you can use crack arrest steel. And these measures themselves, they've been extensively tested, mostly in Japan. And that's why IACS has included these as example measures in their unified requirement. Although it's important to note that these are only possible measures. You can do other things, but it's a bit more complicated to demonstrate they work. Now with the crack arrest steel, the way the crack arrest steel generally works is, as I said, you arrest the propagation of cracks using the plate itself. And you can use the boundary of the crystal grain to act as a barrier to crack development. So if you remember, I said before that one of the problems for the Liberty ships was they had quite coarse crystal grains in their plate. If you have coarse crystal grains, it means you have fewer crystal grains in the plate, which means you have fewer boundaries that could kind of slow the crack down and halt it. Whereas if you have fine crystal grains, you've got a lot more boundaries, and the path the crack takes, it's got to go through there and there and there. And this can kind of arrest the crack. You can also use the orientation of the grains to force the cracks to zigzag instead of developing linearly, which again can slow the crack down and ultimately halt it. Now, so the crack arrest steel, its measure of arrestability is the KCA, or the arrest toughness. Now, IACS have some requirements about what the toughness of the steel should be, and they have two different levels of toughness. They have BCA1 steel, where the KCA value is 6,000, and they have BCA2, where the value is 8,000. 8,000 is tougher than 6,000. And then in US 33, IACS requires that for the hatch combing side plate, if it's EH37, you've got to use BCA2. So this is an even tougher requirement than you would have for, say, the upper deck, which would be EH14. Now, the issue with crack arrest steel is it's quite expensive. The reason for this is you have to do a lot of testing using full-scale model tests to confirm the crack arrest properties. And so that just loads on cost onto the material. I think I've got some illustrations of some of the other things. So as I said, this is the block shift where you offset your welds, and this is the crack arrest holes. So as I said, you have a hole there, mouse hole, and you then fill that with something to make that not have water go through it. And then you have the crack arrest insert plates, and these are all using a mechanical means of preventing the crack from propagating further than it already has. The other approach you can take is a design against crack initiation. So the idea here is that you improve the quality of the welding to prevent the initiation of a crack from a defect in the first place. So IACS talks about having 100% ultrasonic testing, but it also talks about using enhanced NDE methods such as time of flight diffraction or phased array ultrasonic testing. Now, if you're going to go down, now IACS is allowing basically enhanced NDE as an alternative to those mechanical measures of using things like block shift, crack arrest holes and such like. And if you're going to use enhanced NDE, you need to know what your critical defect criteria should be. And so in order to do that, you need to carry out an engineering critical assessment. So this is the determination of the minimum detectable initial defect size. And then you calculate the cyclic crack growth. You then determine the critical crack size. And then you compare the critical crack size with the size of your actual crack after a certain time period. And then you determine a suitable inspection strategy. So we assume imperfections will grow under fatigue. So we use a stress spectrum obtained from a Weibull distribution because you need to use the loads for the ship, and this is all predictive global loading. Wave loads are stochastic after all. You then grow the imperfections under a fatigue sort of scenario, and we assume a two-stage crack growth relationship, which this is all based from a British standard called BS 7910. And so for each cycle that the ship goes through, the load cycle, you estimate the growth of the crack and you increase the dimensions of it, and then you test it again to see whether it will fracture. So you carry out this fracture assessment every time the crack's grown. And basically, if it's above this blue line, then that is not tolerable. And if it's below this blue line, then it's a tolerable defect size and you can keep going. And so And then we have a sort of an LR max, which is this cutoff point that we have. And you can see here we sort of results for each stress cycle, and then the you stop the calculation when it hits this line, and that's where you hope that you've achieved enough life in your ship as compared to the design life of the ship that you don't have to worry about this defect. But that's obviously you take those defects and then you do enhanced NDE to actually go and measure all the size of the defects in the welds and make sure that they're not above that critical defect size. And there are other options. I mean, if you can't quite achieve the design life, then you could potentially do in-service NDE and have to re-weld things potentially. So those are the two kind of approaches that you can take to trying to reduce the risk of brittle fracture. It's not something that can be completely reduced. It is still a probability game, unfortunately, at the end of the day. But you try to do as much as you can to minimize that risk. There are, however, still some gaps. So, for example, in the IACS requirements, there's no mention of what you do if your plate thickness is less than 50 millimeters for EH47, and it's not mentioned in any of the other standards. And the reason for this is no one's really, until fairly recently, no one's really using it for that. So no one's really testing how it can be used. But as sort of ships get more and more optimized, you can kind of predict that at some point someone's going to want to use EH47 for thinner plates. For example, if you had a passenger ship, which they're very weight sensitive, but they also have high stress concentrations because they've got lots of openings, then you could see sort of EH47 being used for around the corners of those openings, and there was all, do we need that to be crack arrest? Is this something we need to be concerned about? At the moment, this isn't something that's been really discussed much, and it's still very much something we'd have to look at on a case-by-case basis but it's coming. This usage is going to get more and more pronounced, especially as the cost of the material comes down. At the moment, the cost of it is what's slowing this development a little bit. You can also see that container ships are still getting bigger, which means they're going to start wanting to use plate thicknesses that are greater than 100 millimeters. And again, the IACS requirements don't really cover that scenario. And this is due to the fact that this scenario has not been tested, so therefore IACS don't want to say, well, this would definitely work in that situation. So it's kind of put back onto the individual class societies. And the other thing that hasn't really been looked at yet is the combination of thick steel plates and low air temperatures. So if you have somebody wanting to have a 100 millimeter thick piece of material on a ship that's going to go sort of minus 40 degrees, well, that could be interesting. And I think in that situation, you probably would want to do a belt and braces approach and just chuck everything at it, because it's something that it's still not really being considered, certainly not in the maritime industry. And then, of course, we have the use of thick steel plates on ships other than container ships, and container ships have a very particular loading pattern. We're always considering hogging, and how can we adapt that to other ship types? Probably easier for gas ships. They've got quite similar configurations, but if someone wants to start using EH47, thick steel plates on sort of tankers, then that would also have to be considered quite carefully. That said, there are other industries that are using very thick steel. The offshore industry already use very, very thick steel plate and even higher sort of strength steels than we use in the maritime industry. So there is, some sort of indications of where we could go with this. But as I said, it's still very much, these are the outstanding issues that we're kind of thinking about at the moment. And that brings me to the end of the slides. So I guess we can move on to if anybody's got any questions. At the moment, no one has asked anything in the chat. It would someone has got their hand up. Okay, so Richard, I will allow you to talk. I can hear you, yes.
Can you see me? Do you want to see me?
I don't really need to see you, but if you want to be seen, then you can.
Yeah, I'm not quite sure how to do that. Yeah, when I was training, the impact test that was used was the ISOLD impact test, which I think was a British test. And the impact test that's generally used now is the Charpy test, which I believe is an American test. Is the ISOLD impact test still used, or is Charpy completely taken over now?
I mean, I'm not completely certain. Certainly, IACS discusses Charpy tests. I'm just wondering if there's any of my materials colleagues from LR that are on this call who might want to put their hand up and answer that question. I think the Charpy test is predominant. Obviously, that's not quite the same as a fracture toughness test. Someone has raised their hand. Yes, I'm going to allow Martin Wright to talk, and he should be able to answer your question. So, Martin, you'll need to unmute yourself. Martin, you can talk now. Or...
Hi, Lizzie, can you hear me okay?
I can hear you now, Martin. Yes.
Finally, yeah, sorry, thanks. Yeah, thanks for a great presentation. Within IACS and certainly class society rules, it is absolutely, for most of the toughness testing, it's only the Charpy test. There are other tests regarding BCA steels, brittle crack arrest steels, and there are other types, but not the one that you mentioned, Richard. But predominantly it's Charpy, yeah. But as Lizzie said, there are issues with Charpy, and particularly for brittle crack arrest steels, measuring the fracture toughness of those steels, Charpy doesn't tell the full story. Hence, there are other tests, particularly some of the large-scale tests that they do. There are developments looking at correlations with small-scale testing, so to do away or to reduce the number of large-scale tests as well, which URW 31 is going through another draft at the moment, so that might be released within the next 2 years to allow small-scale testing, which, as Lizzie mentioned, that will also reduce the cost and accelerate the uptake of these steels as well. So, okay, Lizzie.
Thank you, Martin, for helping me out there.
No, thank
you. Was there anything else, Richard, that you want to ask? Or
if nobody else has got a question, you didn't say that riveted joints were used as a means of arresting cracks.
We don't use riveted joints anymore for other reasons. So whilst the riveted joints are great at arresting a crack, they're not brilliant for the longitudinal strength of the ship. You can't really have these really large container ships, for example, built out of riveted joints. The transfer of the load between the different plates, it's not as efficient as it is with a welded connection. So I don't think there's really any possibility that we could use riveting as the means of preventing brittle fracture, unfortunately.
Yeah, when I was a surveyor, I worked on the QE2, and I was very surprised to see that she had 2 riveted joints in her hull.
Yeah,
presumably for crack arresting, but that's a technique that's no longer used.
No, I mean, we kind of get back to IACS really. So you have to weld it, your ships these days, unless they're sort of historic ships where you can kind of maintain their riveting. And even then, quite a lot of the sort of refitted old ships, they are welding them and then they're sort of making it look like they're riveted. rather than actually riveting them, because it's just so hard these days to, I mean, we don't really have any systems in place for like sort of the quality control of the rivets anymore, and other things like that. So it's become something of a lost art, really, as riveting.
Yeah, I think probably the skills have gone as well. There aren't any riveters around, and there's no means of heating up the rivets and throwing them across the shipyard and that sort of thing.
No, I mean, you have the fun of welding, though, so
if nobody else needs to ask a question, I was very surprised to hear that 100mm steel is being used in merchant ships.
Oh yes, it's particular, because because container ships don't have much of an upper deck, because they want to maximize the number of containers, and then that means that all of the strength in that upper deck and the upper hull girder is being carried by only 2 or 3 meters of deck on each side at most. And then these ships are, they're getting to sort of 400, 420 meters long. So you've got huge global loads going through them. And the only way you can reduce the stresses sufficiently so that they're within the allowable stresses is to increase the plate thickness. And for a while, they moved towards the high strength, using the very high strength steels so that they didn't have to increase the thickness quite so much. But then they pushed the boundary of that, and we've ended up with 100 mil thick EH47 steel.
What about the transition between the 100mm steel and the ship side? You can't go from 100mm.
Yes, you still have to do your sort of your 1 in 3 taper. And so your 100 mil is not necessarily, it's not really going to be your upper deck and your shear strake. It's going to be your hatch combing. So that's where your highest stress is. And then as you go down the ship, you can start reducing the thickness of the plates. So it might be, we might have 100 mil hatch comb, but actually the upper deck might be something more like 80. And then you sort of taper your steel plates into the next thickness.
Yeah, interesting. Yeah, when I worked on the aircraft carriers, we used some 50mm plate for the engine mounts, and I was very surprised that we had to go to that sort of thickness, but that's relatively thin compared to what's being used on container ships.
Well, yeah, 50 mils within the bounds of the normal rules.
Yeah.
And I imagine it's because the engine on the aircraft carrier will be very, very big.
Anyway, I'll shut up and let somebody else ask a question.
Yeah. Well, thank you for your question. Are there any other questions from anyone at all? No? Well, okay. Well, while people are thinking about possible questions, I have a couple of announcements to make for the Southern Joint Branch. So the first one, and I'm quite excited about this, our President's Drinks reception will be held on the 28th of October. This is the first social event that we've had since autumn 2019, when we had our annual dinner. It's the first in-person event we've had since March 2020, when we had a technical lecture on a towing tank at the University of Southampton. And so we'd love to see you all there. Well, actually, to be honest, not everybody. We have limited tickets, but there are still tickets available. They are free. We just want to make sure we can control our numbers. And so, yeah, it's the opportunity for a bit of networking, to kind of meet up with people. There's a drink, there's some nibbles. It's going to be at Revolution de Cuba in Southampton, so it's sort of Cuban-inspired tapas type food. And then after that, the following week, we have our next technical lecture, which will be on large yacht stability on the 4th of November. Which should prove to be very interesting. It's the same speaker who presented on 2nd generation intact stability criteria last year, which was a very interesting lecture, and he's a very good speaker. So I would encourage you to attend that lecture. Now, the President's Drinks reception, there's already details on Eventbrite and on LinkedIn, and you should have all received an email from HQ
inviting you to register. For the next technical lecture, I will send around, I'll be advertising it next week. So again, look out on Eventbrite. If you follow us, you'll get notifications of our events. If you join our LinkedIn group, again, you'll get notified when we post about our events, and also you can look out for the emails from headquarters. This particular lecture, as I said, has been recorded and will be uploaded to YouTube in the next few days. And you can also, if you go on YouTube and you search for the REAN and IMRS Southern Joint Branch, you can find all of last year's lectures. We will create a separate playlist for our different lecture programs, so to make it easier to find them. And yeah, you can check out the previous year's ones if you missed any of them. And so I guess no one else has asked. Someone's actually put their questions in the chat. 6 of them. Well, that's good. So, okay. First one, are there any minimum dimensions required of crack arrest plates? I guess is that the insert plates or just the normal steel? If it's the normal steel, then it's just the thickness of what you would have had without it being crack arrest, and you just make it crack arrest. And if it's a crack arrest insert plate, again, you would make it a similar thickness to the surrounding plate, because that's easier for the weld connection. And we talked previously about the need to taper in, so you don't want to have too big a transition between your different plates. Okay, the next one was about the designation of structural areas. Are they defined by designers or shipyards set by class? They are set by class. So if you look in any of the class society rule sets, but particularly Lloyd's Register's rules for ships, if you look in part 3, chapter 2 of that, you will find a big table, and that table lists all the various structural items that you might find on a ship, and it classifies them. And you can look at that to see what they are. Next question was, is the thick plate material production problematic, or is grain size sufficiently controllable during production? This is one of the ones that's not really my area of expertise again, because it's more on the material side. Martin, if you are able to answer that question.
Hi, Lizzie. Yeah, I think the best way of answering that is the smallish number of manufacturers that do produce brittle crack arrest steels. Their method of achieving brittle crack arrest properties are really a proprietary production method. So, for example, Nippon Steel in Japan might have a different way of producing those properties to POSCO in Korea, for example, and they are two manufacturers who do produce BCA steels. So it's more about fine-tuning the production process to achieve that grain size in a very controlled manner. So it wouldn't be the same production method that you would use on your normal plate steel, your normal, let's say, AH36 or AH36. For BCA steels, it would be an enhanced controlled method, and also the way it arrests the crack as well can be different from different manufacturers. So it might arrest it in different parts of the material thickness as well. So it's quite a, as you would expect, it's quite a science in how that's achieved. But the very quick answer to your question, it is finely controlled, and it is a different production controlled method to your normal steels. Is that okay?
Thank you, Martin. Back to that previous question about insert plates. Okay, the person asked the question was thinking of area. There isn't really a kind of prescribed requirement for the size of the crack arrest insert plates, but you have to think about the weldability of it. So we don't normally want to have sort of weld seams that are too close together. So you wouldn't want to make it only sort of 100 mil kind of deep, I suppose. You'd want to have something that you could actually weld easily in production, but it would also, you'd have to look at the size of the kind of the height, the hatch combing in relation to that as well, and sort of base it on that. But there's no prescriptive requirements for it, certainly. And then there was one last question, which isn't actually for me. It's for Richard, and it's about, was the riveted seam on the QE2 the join between the alloy superstructure and the steel hull? So if Richard's still available.
Just unmute myself. No, it was down by the keel, down by the bilge keel. I mean, one each side.
That's quite interesting. I find it curious, because obviously the QE2 would have been a ship that's predominantly hogging, so you wouldn't have thought that you would have thought it would be in the sort of the upper deck region rather than the bottom of the ship. So it probably wasn't to do with crack arrest necessarily, but for some other reason, which I don't think anybody on here was the designer of the QE2, unfortunately. So
I remember one of the class surveyors saying, the man who designed this ship, he's wearing the belt and the braces. He was German.
Okay. Okay, so maybe it was a sort of a just in case scenario.
Yeah, I certainly assumed that it was for arresting cracks, but I can't really think of any other reason why it would have been done. But yeah,
might have to look into that one. Yeah, you've got
I hope my recollection is correct. It's as I say, it came as a surprise to me when I was surveying the ship.
Well, as I said, yes, that is a curiosity, and one I might investigate a little bit to see if anyone knows. That was the last of the questions. So, and we've pretty much come to 7:30. So thank you very much for your attendance. As I said, I hope to see you at our upcoming events. Even better if it's at the drinks reception where we can actually see you rather than Zoom, where I don't see any of you. And I hope you have a very pleasant evening and a good weekend, and good night to you all.